Good evening, everybody. So, we will just continue the isomerism part where we will see that in case of the corresponding octahedral compound, that we can have two different types of metal ligand arrangements, where the L angles of two different types. One is close to 90 degree and another is close to 180 degree. And if we just consider these two types of angles as the cis angles and the other as the trans angle, and that would be very easy to identify. That means, when we have two adjacent ligands of these, say these two are say chloride for any octahedral compound. If we just simply look at these two positions only, we are not looking at anything else, which will also be true when we have these all other positions are occupied by some other ligand, say some ligand which is also chelating NH2, NH, NH and NH2. If it is chelating, then all the four positions of this particular case are blocked and we will have only the cis isomer. And if we just lucky enough to get the corresponding arrangement of these two chloride as Cl and Cl and this chelating ligand as NH, NH and NH2, we get these as the corresponding trans arrangement. So, we will focusing our attention on Cl metal Cl bond angle and we get two different type of arrangement. In case of octahedral compound also, like that of the cisplatin, we will consider this also as the corresponding cis variety as well as the trans variety. So, what we will just see that in case of cis isomer we have this arrangement, and if we try to rotate it, because along this axis, this is the rotational axis, and if we rotate this molecule along this axis around this particular arrows, so this is the rotational axis. So, NH3 will come over here, this NH3 will go over here and this chloride will go over this particular position. So, this chloride will remain here, this chloride will occupy this position. So, this is the position. So, this is another particular type of arrangement which is different from this arrangement, but again in this particular arrangement also we have the Cl CO Cl angle of 90 degree. So, by different orientation only we have rotated the molecule from one particular state to the other. By rotation only we have generated another form, but the isomeric form of this particular compound is also same, which is still the corresponding cis isomer. But in case of the trans isomer, where the Cl CO Cl angle is 180 degree, again we try to rotate it through this axis, this N CO N axis, we will get the corresponding compound as the other compound. That means, when we rotate, this Cl will come over here and this Cl will come over there. So, we have the Cl CO Cl as the trans isomer. So, this is one trans orientation and through rotation we get another trans orientation, and both of them can be designated as the corresponding trans isomer. So, in case of several such octahedral complexes, we can consider that other form, that whatever we are talking here was in case of octahedral complexes is MA4 B2 type. That means, two of them are of different type Now we just simply move on to the other system where we can have two different ligands again, like A and B or X and Y, it is all same, but their numbers are now 3 each. That means 3 of X and 3 of Y. And what type of possibilities we can have if we can have a type of arrangement like this. And when we consider this type of thing related to the chelating ligand also, that means this ligand, this NH2 NH2 ligand, which is the corresponding ligand which is known as triethylene tetramine, which will be very much equivalent to the donor properties of 4 ammonia groups. So, in this particular case what we see that we can have the 4 ammonia molecule and 2 chlorine, or we can have 2 chlorine atom and the chelating triethylene tetramine ligand, which is also known as triene. Now, we see that in this particular case, that means when we have X and Y, both of them are 3, that means either we can talk about 3 NH3 function and 3 chloride function or the chloride group, or we can have a situation where one is the corresponding tridentate ligand. And also this particular observation is very much useful for us, that since we are talking about the chloride binding, in this particular case if the metal center is there and 2 chloride groups are present over there and metal is balancing the corresponding positive charge by 2 chloride groups, then this compound is present in the bivalent state. That means it is a bivalent compound of the corresponding metal ion. But in this particular case, when 3 of one type and 3 of other, we are balancing the corresponding charge by 3 chloride groups. So, the compound in this particular case is in the 3 plus oxidation, that means the trivalent oxidation state. Therefore, the size of this cation is bigger compared to the size of this cation. So, whatever geometrical isomerism we will be talking about is due to this arrangement around a small cationic species which is trivalent. So, when the formula is X3 Y3 type, there are again 2 spatial arrangements of the ligands. So, we can have 2 possibilities. So, critically if we see the 2 different geometric arrangements, we will see that in one particular arrangement the green spheres are the chloride groups and these are the ammonia groups. So, it is basically a corresponding species which we were talking about, the corresponding hexaamine cobalt 3 chloride. So, here instead of that, in that particular molecule 3 chloride groups were outside the coordinate sphere. Now, all 3 chloride groups have come and entered into the coordinate sphere and bound to the cobalt center by giving 3 cobalt chloride bonds. So, these 3 cobalt chloride bonds basically give rise to a particular type of arrangement where the 3 groups, the 3 chloride groups occupying one face of the octahedron. So, the octahedron we all know that there are 8 triangular faces, and if one of the face is occupied by 3 chloride groups, we will get a corresponding arrangement which is known as the facial arrangement, and the isomer is known FAC isomer. And in another case, these 3 chloride groups, basically what we are doing, we are interchanging this chloride with this NH3 groups. So, if these two are interchanged, these two cis positions, one is occupied by the Cl and another is occupied by the NH3. If these two are interchanged, we get the orientation of these 3 chloride groups in such a one that it is spanning the corresponding meridian of the sphere. The meridian of the sphere is occupying by 3 chloride groups as well as 3 NH3 groups, and in the case of facial isomer we have all cases the Cl COCl bond angles are 90 degree. In other case the corresponding Cl COCl angle, 2 of them are 90 degree, but at least one of them is 180 degree, that means they are trans to each other. So, in case of meridional isomer, 2 groups, which is also true for the binding of the ammonia, these 2 ammonia groups are diagonally opposite, that means the nitrogen cobalt nitrogen bond angle is 180 degree. So, we get the corresponding meridional isomer. So, these 2 isomeric forms are very important, which we are talking about the corresponding phase binding, and if 3 of these chloride groups or 3 of these ammonia groups are occupying 2 diagonally opposite faces of the molecule, we will consider this particular face is capped by the chloride ligands and this particular face is capped by the ammonia molecules. But in this particular case, no such face is capped by either the chloride ligands or the ammonia ligands. It is the meridian of one particular hemisphere is occupied by same type of ligand system. So, from there we just find what we can see for the corresponding chirality of the molecules. So, the chirality of the molecule will be coming for the 6 coordinate geometry also, but for the 4 coordinate as well as the 6 coordinate complexes they exhibit chirality, and these molecules have either no symmetry elements other than the identity element, that means the E operation, or only a CN axis. If they have only the CN axis rather than this CN axis, they do not have any other symmetry element, then we consider these molecules as their corresponding chiral analog. So, tetrahedral complexes can be chiral in the same way than organic compound are. That means, if we have a carbon center, and carbon we all know that is bound to 4 other groups in tetrahedral orientation. In the same fashion, if we can have a center for the metal ion and they have 4 different ligands attached to them, then they can be unsymmetrically chelating ligands also, then that particular arrangement can give rise to some chiral center to the metal ion. Then the square planar complexes can also be chiral, such as the platinum and the palladium compounds of these 2 types, where this is the corresponding unsymmetrical diamine type of ligand when this carbon is substituted by 2 methyl groups, and on the other side we have the phenyl rings, 2 phenyl rings above the square plane, and the mirror image of that, the mirror plane of this particular mirror image is also the other one, and they are not superimposable to each other. They can also be chiral, provided that we can have a different orientations of this group attached to this particular carbon center related to that of our ethylene diamine molecule. Similarly, we just find when we have the corresponding stereochemistry related to the isomers in space, we can find that optical isomerism can be operating over there. We have some effect on plane polarized light, and when this plane polarized light can be moved from one plane to the other, we can have some one particular type of arrangement. So, optical isomers can have opposite effect on plane polarized light. That means, one particular isomer can rotate the plane of polarization in one direction, and the other isomer can rotate the plane of polarization in opposite direction, and these 2 isomers are not superimposable to each other, and they do not have the corresponding mirror image which can be superimposed to the other molecule. So, octahedral complexes containing polydentate ligands, particularly the bidentate ligands. If we have a bidentate ligand like ethylene diamine, it can be seen that the 3 ethylene diamine ligands are bound to the cobalt center in such a fashion that, similar to this type of arrangement, that means that NH2 type of binding, what we are seeing for the part what is there for the triethylene molecule, triethylene tetramine molecule. Similarly, if we have the cobalt center, which is going to form 6 bonds, and we have the ethylene diamine, so this basically coming from, this is above the square plane and this is backside of that particular plane, that means the plane of the paper. So, we have this arrangement, that means one binding of this NH2 group. Similarly, if we have the second one, this is the other one and the third one. So, 3 ligands can bound to these 3 positions, fulfilling the corresponding compound as COEN 2 plus. So, when they are forming this coordination to the metal center, so we get one particular plane, this is another chelate plane and this is the third chelate plane. So, we can have the 3 chelate planes from there, and if we just focus our attention on these 3 positions, basically we see that one particular triangular face. That means we can visualize the molecule like this. So, this is the face, this is the top face. So, that top face is there. So, we have NH2, we have this NH2 and we have the other NH2 from there. Now, we have the other phase, that means this NH2 and this NH2 from the other side. So, we can draw the other 3 phases like this. So, we have this is the visualization of the octahedral geometry once we view through that C3 plane. So, we have 8 such C3 plane and this is viewing the C3 plane through one such planes which are diagonally opposite. That means, these 2 planes basically they are not eclipsed, they are staggered. When they basically move to each other, we get the corresponding trigonal prismatic geometry that we have discussed when we are discussing about the coordination number of other geometry. So, these 2 will be connected by this. So, the second one is like this and the third one is like this. So, we have these basic structure for these 3 planes. So, we have one plane like this and the second plane like this and the third plane like this. So, once we move from here to here, here to here, here to here, we basically get a clockwise movement. So, these propeller blades, this we can consider as some propeller blade type of arrangement. So, when the 3 bidentate chelate rings are bound to the metal center, we get 3 propeller blades and the orientation of these propeller blades can either be through a direction which is clockwise, or it can be anti-clockwise. So, that gives rise to two different types of arrangements. So, when tris ethylene diamine cobalt 3 can be viewed through these three blades, the structure can either be left or right handed with their non-superimposable mirror image. So, when it is left handed, we name them as one particular isomer. When it is right handed, we name them as other isomer. So, if we just consider these arrangements which is left handed and right handed, it can also be considered it as the corresponding helicity. So, helicities are all different. So, when we have this arrangement, so this is one particular type of arrangement, and if we have the corresponding mirror image, the mirror image is this one is the mirror image, and if this mirror image we rotate through some angle of 90 degrees say anti-clockwise, we just get this particular arrangement, but these two are non-superimposable to each other, because this arrangement we cannot put on this which will be similar or same. So, they are providing us some non-superimposable mirror images. So, that is why they should be optically active. So, the upper isomer is right handed and the lower one is left handed. So, this one, this chelate ring is going from here to this, that means the right hand, here to here is right hand, and here to here is also right hand. But this particular one, when we move from there, that means this is in the different direction, that means the face, this is the trigonal face which is facing the viewer. So, this trigonal face is facing the viewer. So, when we move from there, that means we just move from here to this particular face, it is in anti-clockwise direction. Similarly, from here to here is anti-clockwise direction, and here to here these are on the other direction. So, the right handed isomer also requires going clockwise to get from the upper triangle to the lower one. So, if the isomer is of right hand type, that means this one, when you view through two triangular faces, and one such triangular face is such that we can have viewing this particular one which is facing us the way we have drawn it just now, and we see that this is one particular type of NH2 ethylene diamine ligand. Then we have the second one like this, and then we have the third one. So, just we go for a corresponding motion from here, that means the top triangular face. This is the top triangular face, and from the top of the triangular face we just move to the next bite, that means this is the bidentate chelate bite. So, obviously, these two positions are fixed for binding to this particular ethylene diamine molecule, and for doing so we have to move for a clockwise movement. That means, here to here we can go only through a clockwise direction. Similarly, for the second upper face of the triangle, that means the second point, we move again from here to here in a clockwise direction, and the third one in the same way it is also in a clockwise direction. So, when the movement is taking place in a clockwise direction to get from the upper triangle to the lower one, if we have the upper triangle and the next one is the lower one, the prefix for this isomer should be delta. So, the clockwise movement is designated as only the delta isomer. So, this particular case also we can have the different one, that means the binding is not through this. So, this is in the opposite direction. So, upper to lower in anti-clockwise direction, upper to lower again from anti-clockwise direction, and then upper to lower in another anti-clockwise direction. So, this particular movement is going from one form to the other. So, in the same fashion, the left-handed isomer requires going counterclockwise to get from the upper triangle to the lower one, the prefix for that isomer would be capital delta. So, the counterclockwise movement will be designated as the corresponding lambda isomer compared to the delta isomer what is in the clockwise direction. So, this is from top to bottom in counterclockwise direction, then top to bottom in the counterclockwise direction, and then top to bottom face in again in counterclockwise direction. So, this is one arrangement, and the other arrangement is also a different type, and these two things can tell us that how these two arrangements can take place side by side. So, this is for the lambda arrangement and this is for the delta arrangement. So, these two forms basically give rise to the two isomers. Now, we will see how this cobalt 3 can react with ethylene diamine to give us the different products. So, as we have seen in other cases also, that when we have the cobalt 2 and we react with ammonia and oxygen of the air, we get cobalt hexaamine compound which has 3 positive charge to counterbalance with the available chloride. Similarly, this when we react with ethylene diamine, that means ethylene diamine we are allowing it to react with cobalt 2 which is oxidized initially with say O2 or hydrogen peroxide. That means in solution we get cobalt 3 plus. So, we will be considered the way we are considering that the reaction of cobalt 3 with ammonia giving rise to hexaamine cobalt 3 compound. Here also how this cobalt 3 plus can be reacting with ethylene diamine. We can have several products out of these reactions, and where ethylene diamine can be considered as binding of 2 ammonia molecules. So, 2 of these positions can be occupied what we cannot control in presence of Cl minus, that means the binding of the cobalt chlorine bond. But in this particular case, if we are lucky enough, we can get some compound where cobalt chlorine bonds are still present, which can give rise to one particular isomeric form. So, we get the corresponding cis variety where 2 ethylene diamine molecules are bound to the cobalt center and 2 chlorides are still there, which is violet in color, and the trans isomer is green in color. So, we have cis COCl2 En2. Which has one single positive charge, two of these chlorides are in cis position, and this is that ethylene diamine, which is violet in color, and also the trans isomer. Trans means we have 2 Cl over there, and these are the 2 ethylene diamine molecule, which is therefore trans COCl2 N2 plus, which is green in color. So, as we have seen in case of linkage isomers, that the different types of isomers, these are the corresponding stereoisomers also. that the cis variety and the trans variety have different colors, one is green and another is violet. So, how we can identify all these different products even if we are reacting only cobalt 3 with ethylene diamine. So, not only these, that means the cis variety and the trans variety, but when we exhaustively replace all the Cl groups, we get the tris ethylene diamine cobalt 3 compound also, which is yellow in color. So, if we ask now the question that if these two are reacting each other competitively, the chloride function as the ethylene diamine function, how we can determine the number of isomers of each of the products. That means, we have the violet product, we have the green product, and also we have the yellow product. And how we can identify them and label any enantiomers with the proper prefix, that means the delta or the lambda prefix for the corresponding orientation related to their corresponding threefold axis. So, the yellow product is definitely the corresponding COEN whole 3 plus. It exists as an enantiomeric pair, that means one form is optically active, the other form is also optically active, that the clockwise arrangement and the counterclockwise arrangement. So, one is therefore the arrangement which leads to the delta COEN whole 3 plus, where we have the clockwise arrangement from the top to bottom and top to bottom in clockwise arrangement, and other one from top to bottom, that means the green triangle to red triangle from top to bottom in counterclockwise direction, and this counterclockwise direction will give rise to corresponding label as lambda. So, this delta and lambda isomers are there for us in this particular case. But since all these arrangements, like all these nitrogens, are of same type, that means we do not have any other choice for the facial and meridional isomer. They are all of CON6 type. This is also CON6 type, but still within the CON6 environment we can have two different isomers. But in the case of the corresponding chloroderivatives, that means the cis compounds, these are the two cis compounds and this is the trans, and these two cis compounds we can have the corresponding form, that means this is one isomeric form which is in the form which is in the delta, that means which is going from the top to bottom in one direction, and this is also from top to bottom in other direction, and that gives rise to a different type of arrangement for that. So, we get for the cis arrangement these two isomers, and these two isomers are optically active also, but the trans isomer, the trans plane itself is the mirror plane. So, we have only one particular isomer which is optically inactive and which has a mirror plane which is the corresponding plane or containing the two chelate rings. The violet product, therefore, that means the cis product, the violet product is the cis product, and this violet product therefore consists of a pair of optical isomers, and these are the two pairs. So, whatever we find and we identify these compounds, we can label this violet at the corresponding cis dichloro compound, and these two cis dichloro compounds are optically active. One is labeled as delta and the other can be labeled as lambda, and the green product is not optically active because it has a mirror plane. So, the green product, the trans product, is optically inactive product which we get as one isomeric form. So, thus we get the three different types of products and we can label all of them according to their corresponding isomeric form. So, once we determine this particular thing, that means we have the corresponding different forms, we get them as their enantiomers. So, a molecule or ion that exists as a pair of enantiomers is said to be chiral. So, we have a pair of isomers like that of our triskellate or the dichlorosis compound, then we let's call them as the chiral molecule. So, these are the two compounds, there is the corresponding cis dichloroethylene diamine cobalt 3, and this is one form and this is its mirror image, which are not superimposable to each other. So, they are optically active. So, these enantiomers what we get are stereoisomers of molecules or ions. So, enantiomers are therefore we get, they are not diastereoisomers, they are enantiomers and they are also known as stereoisomers, and their molecule or ion itself can be a neutral molecule or can be the cationic or anionic species that are non-identical mirror images of each other. So, you can have the mirror images which cannot be superimposable to the other. So, therefore, we consider them as non-identical mirror images. So, mirror images are not identical. Next, we see that the objects that have handedness are said to be chiral and objects that lack handedness are said to be achiral. So, it is related to the corresponding handedness behavior, that means how the right handed behavior or the left handed behavior can consider the molecule as a chiral molecule, and if that is not there like that of our trans isomer, we consider them as achiral. So, achiral molecules are also known to us. So, when these achiral molecules are there, an object or compound would be achiral if it has a symmetric plane cutting through the middle. So, this trans molecule where we can consider this plane as its mirror plane. So, we have a symmetry plane this we consider as a symmetry plane, and this symmetry plane basically gives rise to a molecule where one half of the molecule is the mirror image of the other half, and which is basically dividing the molecule into two, and that is why the molecule is achiral. So, if such mirror plane or such symmetry plane is present within the molecule itself, it would be optically inactive. So, next what we will see that the molecule like this, what we have seen that the triskellate, that 3 ethylene diamine groups are attaching to the central metal ion, and this is the other form, that means the corresponding mirror image of this, and this one basically giving rise to another form. So, we have this one, the first one on the left, the cobalt center, this is the nitrogen and this is the nitrogen of the ethylene diamine backbone. So, this is the corresponding chelate byte. So, this is the corresponding ball and stick diagram what we get by determining the X-ray structures for the molecules, and the ORTF plot for that basically gives rise to similar type of arrangement, which is the corresponding 3-dimensional arrangement. And this 3-dimensional arrangement once is in our hand and we write in this particular form, that means we write the cobalt and we write the particular square plane, and then the atom which is above the square plane and then the atom which is below the square plane, and then we complete the corresponding connectivity through the ethylene backbone. So, we get this particular molecule on the left and its mirror image on the right. So, we basically get the other as this corresponding mirror image. So, it is moving from this particular one from top to bottom of the triangular face it is in the clockwise direction and it is in the anti-clockwise direction. Then we have the corresponding one which we have seen just that for the other compound which has the symmetry plane, if it is a dichloro compound which is also achiral, and if it is a hexaamine compound which is also achiral, because we have the symmetry plane inside the molecule which is dividing the molecule itself into two, and one half is the mirror image of the other. So, what we see that experimentally how these enantiomers can be identified. The enantiomers have identical properties. So, all other properties are same, only difference is that it can react differently with some chiral substances. If it is reacting for the ligand substitution or any other type, where it is reacting with the chiral molecule, then only it can have a different property with respect to the chiral compound which is coming and reacting with the molecule. And their next other property is that they behave differently with plane polarized light. So, plane polarized light will behave differently with that of the two different enantiomers. So, enantiomers are therefore we call as optical isomers. So, if we have two enantiomers, we will call them as optical isomers, and their effect on the plane polarized light can be measured by using a polarimeter. So, the plane polarized light, if it pass through the solution of these optical isomers, we will see that the plane of polarization will be rotated. So, how we get the plane polarized light? We obtain it by passing ordinary light through a polarizing filter. So, polarizing filter is responsible for polarizing the plane light, that means the unpolarized light. So, if we have unpolarized light which has the corresponding vibrations in all directions, the polarizations in all directions. So, they are not, their corresponding electromagnetic components are not defined with respect to one particular plane. And if we just pass through the polarizing filter, which will allow only because it has the corresponding grid like arrangement, it will only pass the plane polarized light only, that means one direction it will only have this particular light. So, we get the corresponding polarized light, and when this polarized light is passed through the sample, that means the sample which is optically active is kept inside this particular tube, and the tube containing this sample is allowed to pass through this polarized light, and when the light is coming out, there will be some analyzer, and that analyzer will monitor with respect to the light which is entering the solution, that how much movement has taken place. So, the movement of this particular amount, that means the theta amount, the movement of that much will be known as the corresponding optical rotation of the molecule, where we see that the corresponding plane of polarization is rotated by the solution which is present as the optically active compound in the medium. So, that measurement basically gives us the experimental proof or the experimental monitoring for the optical activity. So, through the chiral solution, the molecule which is chiral, and we made the solution, and the plane polarized light is passed through it, and we just monitor here through the analyzing filter, and analyzing filter will measure the amount of rotation with respect to the plane of polarization which is originally present over there. So, if the plane rotates in the right hand direction, we call the molecule as the dextrorotatory compound. So, now related to the corresponding direction of the rotation, we will call as the dextrorotatory compound. So, we have the plane polarized light, if it is rotated in one particular direction, that means towards the right, we call it as dextrorotatory, and if the movement of the plane polarized light, that the vertical direction, always we are considering the plane polarized light which is entering the solution, then if it moves towards the left, this is the movement towards right, and this is the movement towards the left. So, the other form will be known as levorotatory, if the plane rotates towards the left. So, we have the levorotatory. So, for optically active different molecules, the different chiral compounds what we can have, they can also be used for good drug molecule or good medicines. So, different types of medicines also, though we do not have any metal ion present over there, but if the molecule is a purely organic compound and which is chiral in nature, and we can measure the corresponding optical activity by measuring the corresponding rotation of the plane polarized light by polarimeter. The instrument which is used for measurement of those things are polarimeter, and that polarimeter is basically finding that how much movement is taking place, that means the corresponding theta angle for this and this theta angle for this, which can also be represented as the corresponding optical rotation with respect to some sodium D line as the alpha D values. So, these alpha D values through that measurement will consider that whether our compound what we are considering as a good drug molecule or the medicine, whether the molecule is dextrorotatory or levorotatory. And we have seen that some of these compounds, when we have the 50% mixture of dextro and 50% mixture of the levo, we see that most of the compounds where we see that some of these compounds the levorotation is necessary, and levorotatory molecules are the active component for these drug molecules. So, we know that anti-allergic drug, some cetirizine is well known to us, and this cetirizine molecule, previously we do not know what particular form, whether the dextro form or the levo form is useful. Now is well known that the levo form is active form, that is why in the market also the levocetirizine is also available, and this levocetirizine is labeled and which has the corresponding measurement for this optical activity, and we prescribe this as the corresponding molecule as the levocetirizine. So, when we have both of them together, we consider it as the racemic mixture, and that racemic mixture is not very much active for all these cases, because only 50% of the molecule is only working, the other 50% is not active and which is not useful to our system for our treatment. So, chirality is therefore is defined as the chiral molecules which have a degree of asymmetry that makes their mirror images non-superimposable, and molecule can be chiral only if it has no rotation reflection axis. That means, you do not have the SN axis, rotation followed by reflection. If this axis, if it has no rotation reflection axis, then only the molecule is optically active and chiral. So, chiral molecules either have no symmetry elements and can have only axis of proper rotation, that we have also discussed earlier. So, if we have the combination of these chelate rings, what we see that handedness of and propellers and helices. So, if we have the front view is like this, the propeller view, and the side view of this is that if as the bolt face is side 1, then in this particular phase is one form is moving from one direction to the other, that means it is in the lambda form which is in the left hand direction. So, it is in the left hand, and when it is in the other form, that means when it is in the right hand direction, we get at is as the corresponding delta version. So, we already discussed all these things, that means the cobalt tris ethylene diamine, it has 3 bladed propellers and looking as a molecule down to the threefold axis. So, what we have seen that either we can consider it as these blades or this one or this one or this one. So, when we have this, that means when we consider this as from the connectivity from this side to this side, or the connectivity from this to this and this to, so it is in the counterclockwise direction. So, we have the lambda isomer, and when this connectivity is going for in other way, that means when we have the isomer in this form, that means this is the top triangular face, and this top triangular face is going from this clockwise direction, from this nitrogen to this nitrogen, from this to this. So, this is another diagram for getting this particular arrangement. So, any of these arrangement is fine, either this arrangement or in some hexagonal geometry also can tell us whether we have this particular drawing or this particular drawing for lambda isomer and for delta isomer. So, in all these cases, it is important that viewing through these triangular faces, how this can accommodate the lower face and how they are connected, if they are connected in clockwise direction or if they are connected by counterclockwise directions. So, one such good example made by Jorgensen, which is a famous person who did all these molecules for so many years and described the molecule as hexol, and this salt can be prepared by simple heating the corresponding diaco compound of the tetraamine cobalt 3 with dilute base such as ammonia. And when we get this, that means when we have the cobalt, important thing is that we have NH3 So, if we take the cis compound and if we heat it with ammonia, then what happens? So, the compound which next get can be precipitated as its sulphate salt, because if it is cationic we need to have some anions to get it precipitated. So, the reaction is very simple, the 4 molecules of this is reacting, giving a tetranuclear compound which is a big molecule basically, and which has 6 positive charge with the liberation of 4 molecules of these amine ligands as ammonium ion and 2 of them as proton and 2 water molecules. And these salts exist as dark brownish violet or black tabular crystals, and the salt has low solubility in water. So, how these are forming? So, the tetranucleation what is forming over there is due to the corresponding condensation reaction what is there, that means it is can be isolated as yellow grey chromate or hexachloroplatinate salts. So, this is the compound what is forming over there, like the tris chelate now is a purely typical inorganic compound, no organic ligand is present, and this mononuclear species, that means the tetraamine cobalt part is behaving as a bidentate ligand from this side and from that side. So, it is a very unique tetranuclear compound where this particular part, that is the complex itself, the 3 surrounding complexes are behaving as 3 bidentate ligands. So, that is why that gives rise to the corresponding optical activity for the molecules, and the salts were first synthetic non-carbon containing chiral compounds, and the sulphate salt has this particular formula because it has 6 positive charge. So, 3 units of sulphates groups should be present over there, which can crystallize it as a unique tetranuclear compound, which is optically active and which is purely inorganic in nature, because it has no organic ligand present in it. Thank you very much.